I forgot I was muted.
Oh, sorry. I think you can start
That's
now.
fine.
Yeah.
Yeah, sure. Thanks. Okay.
Pavan, could you please start the recording?
Yeah, begin.
Okay, bye.
Okay. So I think I can start. Okay, great. So let me just start with a brief recap, and then if you have any question, you can ask. I mean, if you have something. So as we have seen yesterday, so this is kind of the structure of the neural network. That's what we were discussing so far. And this is, say, in this case, this is my input layer, and this is the output layer, at least in this picture. Just to show what are the things. So we have defined something like a weighted sum, which is depending on this weights and the values of this yi's. So that z was wj yj plus b. Sometimes I use this w. Normally people use omega w as weight. I just use omega or w interchangeably. So if you have any problem, let me know. And then I have defined that whenever I will use, I have to talk about what are the parameters of the network, the full set of network. I will always represent it by theta. Theta is set of all the weights and biases, every one of them. And f is some activation. F is some activation function. This activation function can be anything in principle, just have to be nonlinear, and it's very problem specific, that we also have discussed. And then for each training, so this is as we are talking about supervised learning, while training, you have to punish the network in some sense, or you have to say that whatever output you are producing, there is a cost associated with it, and that is something called cost function. And this cost function is some function, it can be anything, of the network generated output minus the target output. Last time we discussed a cost function, which is normally we would use, which is the mean square difference between the network generated output and the target output that you have. And as we have also discussed, so since in training we have a lot of set of data, like 1,000 in order of 10,000, 20,000 data. Around that time, calculating the cost function for all those set of data is normally computationally very inefficient. So what we do is that we just sample out a smaller fraction of the full data and just calculate cost function over that smaller function. And then we update our network parameter like this, so that this c cos theta gets minimized. Okay, this eta guy sitting here, that we also mentioned as learning rate. So these are the terms that we learned yesterday, which is weights, biases, what are activation functions, and learning rate and cost function. Okay, now let us look at in more details in this learning rate and all this business, and how to train your dragon now. So in the feed forward, so first thing is feed forward. Feed forward means whenever you are here feed forward, that means they pass through the full network. So from the input to the output. So you start with some input, okay, and for whatever be the values of W's or biases there, you calculate the output, okay, and calculating that output is termed as feed forward. It's just going from the input to the output, okay. Now to go further, I would start with some set of notations and all, but before that, if you have anything to ask or any query from the last yesterday's talks, if you have something.
So, I have a question.
Yeah, from
This
go ahead.
this input, when you say input, is it the training data input, or the input you give to get the final result?
Right. So then for network, when I say input, it can be training or final set, does not matter. Given an input, it would get an output. So training means given an input and the output, you are changing the parameters of the network. When you are actually changing the parameter of the network, that's the training phase. And when you are not changing the parameters, whatever output it gives, you just take it with good faith. That is the you're getting the results or the predictions. Okay. So whenever I say input and output, it can be anything in principle. Okay.
Okay, thank you.
Input is just some values in the first layer and getting the output. So feed forward is for a or whatever value you are putting in the input, getting the output. There is no change of parameters or anything associated so far. Okay, I will go through the steps now.
Okay.
Okay, great. I'm assuming you don't have any questions, so I will just start with setup notations. Or is there any question? I can still hear some noise. Or no,
Uh,
just from
uh,
Pawan.
yeah, so I
Okay.
wanted to say your
Yeah.
mic is touching somewhere and it's noisy.
Oh, is it fine now?
Yeah.
Is it better? Okay, great. Yeah. So this before proceeding, we need to do some setup notations that we also used yesterday. So YKN means that this is the value of the neuron K. Sorry, the value of the neuron K. Yeah, value of the neuron K in the nth layer. Whatever the upper index is always the index of the layer, and this is always the index of the neuron. And weights jk is basically between jth neuron in nth layer to kth neuron in mth layer. Okay, but normally, I mean, or in the full set of talks, whenever we have a network, normally each adjacent layers are only connected. So there is no connection between, say, first layer and the fourth layer or fifth layer. There is no connection like that. So normally this weights, whenever I say talk about weights, normally these weights are always in this form, where this n plus 1th layer j and nth layer kth neuron is this weight denotes the connection between them. Okay, and bkn, again the same notation. So that means the kth neuron in layer n. What is the bias of that kth neuron in the layer n? And zkn is the weighted sum evaluated at kth neuron in layer n. Okay, so as we have seen for several times, so now the weighted sum for, say, some jth neuron in n plus 1th layer is basically this one, which is sum over all the weights and the neurons before it, nth layer, and just add the biases here. Okay, and the output of that neuron, the jth neuron at n plus 1th layer, is this thing, some f of zj n plus 1, where f is some activation function of your choice. And in this notation, n equal to 0 is always the input layer, and n equal to n maximum, or sometimes I will use capital N, is the outermost layer. Okay, that's the whole notation. Now, one of the advantages of using Python is that normally Python, I mean, is basically slower than standard C++ uh, or C, of course, uh, most of the time. But the advantage is that people have produced so many packages and all that it's now easier to do, at least at this point. And it can process things in batches very quickly. Or you need to know very minimum coding to actually do it. That's why probably most of the physicists are now doing in Python as well. The theoretical physicists who are jumping in this field. So in Python, this whole thing, the z calculation that you have, it can be written as simply as that. You can just write NumPy is the numerical Python library that's already is very much used, and you can just install it in your machine. And there you just write NumPy dot with W and Y and B. Now you see this Z is basically is a vector, is a one-dimensional or just a set of a column vector in some sense. If you as in out, this W can be thought as in out cross in in. I mean input dimensional weight. Y is of course the vector in. That's why you can take the dot, and then B is the output. Okay. Then, as we have also discussed yesterday, for mean square deviation kind of things, what you can write is a cost function like this. This half factor will be clear in a minute. Or you can throw the half factor as well. Machine can handle that. Anyway, for the calculation simplicity, now on I will just put half here. And we have discussed this part as well, that the cost function is basically you have to average over all samples. Okay. What does it mean by the training data is that for a given y input, you already know what should be the output. These are the known points, known data points kind of thing. Okay. And then what you're trying to do is that you have to figure out a y out, which is basically a function of Now all the network parameters and all with the neural network output, and you want to match that. That y out should be this thing. And normally for one input, one output kind of situation where you have only one neuron in the input and one neuron at the output, there it's basically a curve fitting problem. It's just a regression problem, and you can see these kind of things. And that's the simplest version of it. Now what we have started discussing last time as well, that we want to minimize the cost function by doing the gradient descent. There are other processes as well, but I will focus on the gradient descent only in this case, in this talk at least. So this and also I said that sampling over all the data set, all the training data set is very computationally inefficient. So you would sample over some minimum number of things, and that is called that's why this is called some stochastic gradient descent. Now the issue is that with the stochastic gradient descent, I mean that, as I've said, that averaging over a huge training data is computationally inefficient, and that's why you are doing this thing to make out some parts of the data to do your bidding. And whenever I write C tilde, that C tilde is the average there. I mean, averaged over the cost function over some sample, not over the full data set. Okay. Now you see, in normally when you do numerical differentiation in numerical simulation or whatever you have, normally what you do is the first principle of differentiation. You just write f of x plus h. Let's say you want to get f prime of x for some function fx. You can use f of x plus h minus f of x by h, or the different kind of notations are there, and then take h to be 0. I mean h goes to 0. That's the definition of differentiation, and that's what you normally use in numerical methods. And here also you can do that in principle. What you can do is that you can just change your theta j by a small number and see how your c theta changes, right? So to do that, what you have to do is each time you have to do a forward pass, right? Because the cost function is only generated at the output. So if you just change one of the parameters and then you know how it affects the cost function, you have to actually do the full forward pass again and again for each parameter, each weight or each bias. Okay, so that is very computationally taxing. So what we do is that the following algorithm. So let's say you are interested in calculating this number, which is the cost function, differentiation of the cost function with respect to some weight on bias. It's somewhere in the network. The star denotes it just somewhere in the network, wherever it is. Okay, you want to calculate this thing. So theta represent both weights. It can represent both weights or bias. So theta star is some weight or bias in the network inside, and then you want to calculate what is this del c del theta star, because this is what you need. This del c del theta star along with the learning rate can tell you how you have to adapt your weights or biases as the training goes on. So to get to that bottom of it, you just say, let's say we start with two-layered network where I have this output and I have this input. Simple. Now here my z is w1 y1 w2 y2 plus b, and c theta is half fz minus fy12 square. This f is basically your target value, or this is what you want to achieve. For given y1 y2, you know that what should be the value of the neuron here, and that is your f. Okay, and small f is basically the value that this neuron is giving you now. Now if I do del c del w1, that is just this thing. There is a y prime thing. Y prime is just right. Sorry, there's a del z del w1 with respect to the w1, and that is y1. Or if you want to do with respect to b, that is this thing. Okay, so you see this part is more or less common. This fz minus f prime. This is common, and this thing gets changed. Now, so far this one is only for a single layer. A single layer in the sense there is no hidden layers. You have only input and output. There is nothing inside. Now say you have a network with multiple hidden layers, each layer consisting multiple number of neurons and multiple number of nodes, and how to proceed with the calculation. So to do that, to begin with, you say that you the c theta, which is the full cost function, which is getting averaged over all samples, you say the C theta y in is basically cost for a particular input. So for a particular input, for one input in your training set, this is the cost associated with it. Okay. So you want to calculate this guy, del C theta y in by del theta star. Theta star is somewhere in the network. So to do that, of course, you'd get this result first, because where this n denotes the output layer. So because the cost function, you see, is basically starts at the very end. So you can begin with writing this. So and this is the desired output of the jth neuron at the end. That means that whenever you say that you have a target result, so that means if your output has 5 nodes, let's say, then for each 5 node you have a you know what should be the output of each 5 node. So this fj denote those things, each j at the last layer or the output layer. So that is simply this. Let me know, by the way, if you're not getting something, then I can just repeat here. Then once you have that, this yj, sorry, right. So once you have this thing, you can now see that this yjn is also that this yj is something like this, f of zj, this yj, and since this is right here, so yjn is basically f of zjn. So that means here this different derivative, you can write it like this, that f prime z and del zjn del theta star somewhere. Now we can use our standard chain rule. Now chain rule is saying that this thing you can write as in terms of the variables in the previous layer at the n minus 1th layer. Okay, so you can write del zjn del ykn minus 1 del ykn minus 1 del theta star. Okay, now see, good part is this thing that we already know, del zj del yk is always wjk, which is the weight between the the last layer and the layer before that. Okay, so you get this thing, and now you see at the end of the day you also generated this guy, which is del zk n minus 1 del theta star. You can again do the same thing here. This thing can be calculated, that means in terms of the layer previous to it, n minus 2th layer. Okay, so in general, what you can get is that for any layer n, your del zj del theta star looks like this. Okay.
Argo,
Yeah, super.
at some point it should stop, right? Because theta star would have occurred after some point.
Yes, I will go there.
Okay.
Yes, yeah.
Okay.
Don't worry. So far, this is theta.
Can you? I just missed that part. What exactly was theta star again?
Theta star is some variable, some weight or bias in somewhere in the network. I haven't specified where is that yet.
Okay.
It can be anywhere. I just want to calculate the derivative with respect to that, because at the end of the day, I need to calculate the cost derivative of the cost function with respect to all possible weights and biases. This is just one of them.
Okay.
And Subbu is asking, I will go there, Subbu. Okay. Now, good. So what you have is this thing for any general zjn with respect to theta star is always looks not always. I'll come to that, but it does look like this. So this n and n minus 1 layer are connected. So that means that each pair of layers, n and n minus 1, contributes multiplication with the following matrix. I can write this as a matrix, this mjk, which is multiplication of these two things, where this f is the derivative of your chosen function, and this is the weight from here only. So this part, I say that this is some form of matrix. I will go to the meaning of this matrix after that, but this is say some matrix. So if I have this matrix written, that means that I can do the repeated multiplication going down the net, starting from the very last and then going down the net. And as Subbu was asking, I will always hit the n tilde layer. Say this is my situation. This is n tilde minus, this is say my n tilde minus 1 layer, and this is n tilde layer. This one is n tilde layer, and theta star is in between that. So once I hit that layer where theta star belongs, basically, I will end up with this kind of relation. Okay, because after that there is no point of it. So del zj n del theta star, you see that this is the result, and there this is like the multiplication of matrices starting from the up to this layer, to the n tilde layer. Okay, so with all this thing, what you have is that finally, if theta star is a weight at that n tilde layer, you will just put this derivative to be yk, or if it's a bias, it's just 1. Now, this whole thing is called back propagation. What is the advantage of the back propagation? I mean, this is just some sort of gymnastics so far. What's the point of it? Now, the point is the following: that you can follow these 3 steps, and that basically fixes all your calculation in a single go. So while doing the forward pass, what you can do is you can already calculate some variables that you need for back propagation, and once the forward pass is done only once, your back propagation results are already known. How do you do that? Is that you do this following 3 steps, and once I share the notes, you can make yourself more comfortable with these 3 steps and why it works. So initialize some deviation vectors, which we just call it a deviation vector, which is just this part. This is the full thing, whatever you got here. But yeah, this one. Yeah, here this is the full thing minus this part, this derivative. So this is the matrix kind of thing. This thing. So this just defined as the deviation vector, this thing, and you calculate that in the very outside layer, the last layer. You see, all of these things are known at the very last layer. You just do this calculation, because if you know f as a function, because f is some activation function that I'm giving, so f prime as a function I already know, and in some sense I'm also providing the network with that. So there's nothing much, nothing extra that I need to calculate this deviation so far.
Sorry, Argo. What was
Yeah.
Fj?
Which one? This thing, right? So
Ah.
for each output, so for say this is my output layer, this is my output layer. Okay, then network might generate at the output layer. Network might generate say 0.1, 0.2, and 2.0. Okay, but what you want to have, because it's a training phase, what you wanted was that this should have been this should have been 0.2, this should have been 0.1, and this should be 3. Okay, so these are my yjn's at the last layer, and these are my fj's at the last layer.
I see. Okay.
Got it? So fj's
Yeah.
are the given data, coming from the given data set. Is it fine now?
Yeah. Sure.
Okay, good. So once you do this calculation, this part you can just calculate without doing anything if you do the forward pass. Now for each layer, of course, starting from the very last layer, you calculate all the derivatives of the cost function and store it in your memory. And this derivative is nothing but this one, right? This thing, del j, del zj, theta j. And once you are done with the last layer, say you have done this calculation, go to the next layer. But before going to the next layer, you just update your del j new as this thing. Okay. But
Argo,
yeah.
I'm still confused actually.
Yeah. Okay.
Whenever you evaluate the function, it is with respect to z, right?
Which one?
Function. Whenever you have a function, the argument is z, right?
F of z, yes.
Why do you have fj of y now?
Oh, this is just y in. It's
Oh,
written.
input.
So-
I see.
Input is
So that
just
fj does not
y.
depend on level, Subbu. That
Right.
fj is not the function of level. It's the
Right.
full
It's
final function that you want to approximate.
final function. Yeah, Subbu, and I think he was just confused with that. In, he didn't read the in.
Okay.
With
It's the first step.
Right. It's a very, and it will always be the same, because this is the target
Okay. Yeah.
thing,
True,
and you're
true.
keeping it, so it's a constant in some
Okay.
sense.
Got it.
So
Got it. Okay.
so there will be nothing that works here. And once you do this, here you go down. While going down, you just get these things as well, and just update the values of the delta j by this thing. And I will urge you guys to go through the notes and just make yourself comfortable with the fact that if you do this thing, you know at the end of the day all the derivatives. So doing a single forward pass, what you can store, you can just store this derivatives with respect to each theta k with this process, with this value which we just derived, And if you do that, you know all the derivatives. So you don't need to do for each derivative. You don't have to do a forward pass and calculate everything. Okay. Now that's why this backpropagation algorithm was kind of the backbone of further developments that happened after 1960s or around, probably. Because before that, the backpropagation, people were not even including hidden layers and all. And this backpropagation algorithm was always like a numerical differentiation, where you change the weights or biases by some certain values, and then see how does it affect the cost function, and then update it. And that was very time taking, because for each weights and bias you have to do a forward pass. That's computationally expensive. So backpropagation helps you with all these things. And
Can you say what back propagation is again?
okay. So backpropagation is just a set of algorithm. What you want to do is that for a given input, first you want to calculate what is the output for the given input with with already existing weights and biases. Then you want to match how far is it from the target that you have. Okay, and that gives you some measure. That measure is what we call the cost function. Now you want to adapt your weights and biases such that that cost function gets minimized. To do that, what you have to do is that take a derivative of the cost function with respect to your weights or biases. Okay, and that is called and updating that is called backpropagation. This particular algorithm of doing backpropagation, where you are updating your weights and biases after the forward pass, that means after getting what is the value and getting what is the mismatch or what is the error in getting the desired output, you are adapting your weights and biases. That's called backward propagation. And this particular algorithm that I am showing is most efficient backpropagation algorithm. Is that fine?
You get the derivative, and then you change the thetas by eta times
Right.
this
Exactly.
derivative. But what is eta?
Right. Which is eta is something that you are giving by hand. Yeah, Python will be coming in a very short while that you will understand. Eta is something that you are giving by hand. The Python codes are coming in the next section, so you would get all the answers there. Okay. Now, there are some certain things that might be interesting. Some of you, that this gradient calculations physically ask this question, that how a small perturbation in the weights or bias affect the cost function, right? I mean, that's it. That question should be very trivial. But see, this is the same question as asking the that we ask in the physics about the response function, right? So normally what we have is like a Green's function that we define. Green's function is basically that how a small at some disturbance at some point, say wherever it is, and how does it affects the point after that, or somewhere in the vicinity. As I wrote it here. So at some point f, due to some small change in point I, how that thing is propagating, that is the Green's function, and that can be decomposed as sum over all disturbances that propagate to some intermediate point j, and then from j to f, right? So very crudely, you can think of this like this. And now you see that m thing that we have, that's capital M that we define. Yeah. So this capital M that we define, and then multiply that each layer by layer. See, these are all between successive layers. So in some sense, this is like my Green's function, and this is how things are propagating. So I just wanted to, through these things, I just wanted to keep on reminding there are some parallels with the cost function with the Lagrangian, and now you see this whole backpropagation algorithm has something to do with Green's function and all. And people are trying to build up some. I'm trying to go in this direction as well, where they're just formulating neural networks as field theory problems itself. But probably that can be, I put it in some other lectures. Now let's see. Now see that there are a lot of calculations and all that you have to do this backpropagation and forward pass. And although I mean I have a code. If you are interested, I can share that code with you guys at some point. That just does all these calculations without using any package. But that makes your life a bit complicated while you are writing those things first. But once you write that, after that you can use it. In modern day standing right now in 2022, things are very smooth. your life is actually very simple. You don't have to know what is backpropagation, how things work to actually build up a neural network and train it. And you can do this thing in Mathematica as well if you are familiar with that. But I'll just include. Um, I will just here put out Python commands because I think that at this point, if you really want to, some of you really want to go into the details of what exactly is going on. Mainly, people are working on Python, or yeah, Python mostly. I haven't seen anybody putting out any other codes so far, at least in high energy literature. So Python, I would suggest something that you can pick up. It's very easy language to pick up. So so say you want to reproduce a network which have this number of layers. So the input is 2, input layer is 2. So then the first hidden layer 64, 28, 64, 1. So in some sense you want to have a network like this. So these are say various connection, and then this is your input, which is 2. Then this is say 64 number of nodes are there, 1 2 3 4 64. This is 28, this is 64, this is 1. Okay. This is something you want to build up. Now to do that in Python, it's actually very easy. First you have to install Keras, or just install TensorFlow that already includes Keras. That's a very high level library that uses this thing. You just have to say, I just named it as JAL ST4, whatever. LETHEP was too long, so I just wrote ST4. So this is the name of your network. You just write sequential like this, and sequential means that standard layers, as we have discussed. So where adjacent layers are connected, you can have different topologies for these layers, but we are not going there. So you can play around with all these things, whatever I am saying. But right now, I just want to discuss a very basic neural network, which helps us. That's it. So JAL ST4, if first say that this is a sequential network in this line, and then you say that JAL ST4 dot add means just add a dense layer with 64 values, where it takes a input 2, where the dimension of the input is 2, and the activation function of everybody is ReLU. ReLU is rectified linear units. Oh, I forgot last criteria. What is ReLU? So that's just rectified linear units. I showed the function if you guys remember. So it's just this thing. It's just 0 and then
Argo,
LD. Yeah,
what is input dimension? What does it mean?
yeah. I will. Oh, that the same. Just as shown, right? Then this is a network where you want to have a input as 2. So input does not have any activation functions or anything, right? Input is just some number that you are providing. So that is 2, and that is getting specified here. That's the first layer in the network, and you are saying that this layer has 64 nodes, and that gets a input which is 2.
The number two,
Number 2, yeah, number 2 in a sense 2 nodes are there. So it's a array
or,
basically.
or nodes. Okay, okay.
Yeah,
Got
it's a
it.
number
Thank
of nodes. So 60. So I should be drawing this thing again. So this is, so far what we have built up is this thing. So far it just know that this is 64 number of things. That's what he knows, or he, or this person, this network person knows. Okay, so far.
Can I ask a quick question?
Yeah,
So, what
yes.
is this gel underscore SU? Is that like some particular type of data structure, or is it
Which one? Which one?
the thing that you're defining in the first, something equal to sequential of?
Ah, sequential.
Is
It's
it
just sequential. Yeah, sequential means that the layers are just the adjacent layers are connected.
correct? Correct. No, no. The, I understood the meaning of sequential. Is there this thing a particular date? Like, is it like a list or a stack, or I mean, is
No,
there
no,
some
no.
particular? There
It's
is no such.
no. It's just, yeah, you are basically so far in this part of this code, you are just setting the attributes of the network. So first attribute of the network is that it's a sequential network. I haven't told what is the size or anything here. I just said that prepare for preparing a sequential network where just only the adjacent layers will be connected.
So sequential is a
Oh,
function you defined, is it?
Right? No, sequential, it's not. It's a predefined thing. So wherever here, whatever I'm using, there's nothing that I have defined. This is already predefined in the TensorFlow package. I'm not doing anything. That's why I said that once you have a TensorFlow, you can just use sequential. It knows what is sequential.
Okay, okay. So, and when you define this input shape equals 2 comma, I mean, that comma, what else could you have put there? Like,
I could have put there is 2 comma 1 or anything. I mean, I could have put anything there, but
okay,
normally it's in
okay,
for this is like a 1D problem. I'm not doing anything.
I
So
see.
so there are
Okay, okay,
different kind of networks where you can actually have you can let your the network to think that this input is have some 2D shape or 3D shape kind of that thing. So
okay,
that's why this
okay,
is a very generic part, but you can just use this as well for the time being, or for this kind of networks. Whatever we will use, you don't need to specify anything here. Okay.
okay,
Mm. Great, great, good question. And input shape, as Pawan, you're asking, this input shape, sequential, dense, add, activation, everything is defined, already defined in the network. If I would define some function, I would let you know. So far, I haven't used any customized thing, unless just the name of it is something that I customized, nothing else. Okay. If you have the TensorFlow package, you can just use these commands. That would work.
Okay, okay.
Okay, great. Now,
Arghya, so like
yes.
sequential, what are the other things that you could have? Like,
Right. So I'm not an expert on all those other things, but there are what you can do is this. All these things you can, in fact, you can do it by hand. And rather than having sequential, I forgot the other name, but there are some layers where you have, adjacent two layers are connected to the first layer. I mean, n and n minus one and n minus two are connected. Those can happen. And also there are something called
and so
convolutional.
are there oh sorry, are there special problems like where those are better? Like,
Yes,
uh,
yes, there are special problems where those are better. For example, there is something called convolutional neural network, which I would just let you guys know after some time today. That's one of my target. So at least briefly outline it. So in convolutional neural networks, what you have is that you have several networks in the same layer. I mean, several layers, several set of neurons in the same layer, each for different feature extraction. TensorFlow, all these packages are very, very much generic version package. You can do all possible networks with this thing. So to do this simplified networks, I'm just writing what you should write very minimally. But yeah, I forgot the name slightly, but I will come back if I remember it. I will let you know what are the other things on sequential. Or you can just search in TensorFlow. Just write sequential in TensorFlow or something in Google. You can get it. But I will let you know what are the other things. But normally, most of the times, what I have used so far is only the sequential part where the adjacent layers are connected. That's why I don't even bother to check. But anyway, but those things are there, as you are asking. Those things are there, and they are very much problem specific. And yeah, sometimes those are useful, but I haven't used personally. Okay, good. So dense means that these networks are this all these layers are densely connected. Densely connected means there are other possible connections that is there. Once I do this convolutional layer, I will let you know what are other layers. One of them is conv layer, something called convolutional layer. But here the dense means do I have dense? Oh, I'll let me just show the dense layer. Right. So this is the dense layer. Dense layer means everything is fully connected. Okay. Every guy is connected with every other guy. Each neuron is connected to every other neuron. So that's what I meant by dense layer. Okay. Good. So right. So dense, for the very first hidden layer, you have to specify what is the input for the very first layer, as Shubho was asking. And there you just said that input shape is 2. So that means create a first layer of the first hidden layer as or first layer, create a layer with 64 nodes, which takes input from two nodes, previous two nodes, which are input nodes, and activation function or the f function that we are doing, small f, set that to be ReLU, rectified linear unit. Then you want to add this layer, 28. You just say javast4.add dense 28 activation equal to sigmoid. Now here you don't need to say input shape because input shape is already defined in the previous layer. So you don't have to specify what is the input shape here. Okay, and I just used different activation function for each layer just to let you know that you can do that. But normally in principle people just use one activation function. for all the things. So here the activation for 28, I said sigmoid. Then you create this 64. You just said again dot add 10 64 activation equal to 10 hyperbolic. And at the last layer, this one, you can just say dense 1 activation is linear. Okay, so it just created something where it knows what is the input layer, and it does not know what is the output layer yet. You can add more layers. Does not matter. You can just keep on adding jal underscore st4 dot add whatever you want. But say we stop here. So far we are thinking about this network itself. 2 64 28 64 1. Now, dense I have already explained. Relu I forgot last day, so that is just rectified linear units. Good. Now, what you want to do is that now you want to initialize the network with some random weights and biases. So far, I just said what are the number of nodes, nothing else, and how those nodes are getting connected. That's what I said so far. Now, to initialize the network with random weights as well as biases, and make it ready for all these operators, all these matrices and all that you need for backpropagation. At the first place to do that, what you have to do is compile the network. We call it compiling the network, and that's also very easy. You just said that okay, Dali st4.compile and dot compile with the loss as mean squared error. Here also I have not defined what is mean squared, mean underscore square underscore error. That is already predefined in the TensorFlow package as well. And you say what is your optimizer, and this optimizer forget why I have included. Don't worry about why I have included this part here. It's something called Adam, because I'm coming to what is Adam, and there is this Adam takes a argument which is I just said LR, and that is the learning rate. So learning rate is the initial the learning rate that we are talking about, this eta that we talked about. Okay, that you have to fix by hand, as I've said. So while compiling, you have to say what is your learning rate. Okay. Now the Adam is something that if you remember, what does this learning rate do? This learning rate takes first start with the cost function, do the differentiation, and you modify the cost function to some to go to the some minima, right? And each step is basically parameterized by eta. But it may so happen that there can be a better learning rate. Whatever you have provided, there can be a better learning rate which provides faster convergence. Okay, so Adam is one of the optimizers. That's adaptive something, I forgot the name again. But this Adam is something very modern. People are using Adam now. What Adam does is that you start with some initial learning rate that you specify here, and then Adam keeps it modifying as the training goes on to get faster convergence. You can tweak what are the parameters of Adam and all, and those are very under the hood things, but I'm not going there. For a simplistic scenario, you just put Adam and then what is your learning rate. Okay. Now, once you have that, you should also have, so you have a network now. This network knows what is the cost function. You have told it what are the activation function, what is your initial learning rate, and how do you want to change your learning rate as things evolve. These are all the things that you told the network. Okay, and now what you have to do is now you want to train the network. So before training, what you have to do is that you should have a set of data. For example, say you need the data of a person's say foot size and glove size. That can be 2 data points, and the output is that person's height. Okay, so 2 data, say, because in this network there are 2 inputs and 1 output. So for example, say that the 2 data and 1 output set is basically my shoe size, and not mine, all of our shoe sizes, glove sizes, and what is our height. Okay, now this set of data 2 to 1, this should be, let's say this X is your input set of data, Y is the output set of data corresponding to each input. Okay, they're formatted like this. So that means the first data in X, first data in Y correspond to the first data in X. Okay, so what you have to do is there are several ways to do this training things and all, but I would suggest just go use this thing .fit. It shows you all the graphs as well. I mean, how the training is getting progress, all the nerdy details that you want to have, all the things are there if you just say .fit. So you have to name your network Jali underscore st4.fit, This is the input. This is the output. What should be the output? Then you say batch size. I put it wrong. Batch size. Batch size is the thing that I was talking about sampling. So I said that you don't do the cost, calculate the cost function over all the training data. You just calculate the cost function over some short number of samples. So that short number of samples you are specifying here, say 5, for whatever be the size. I just put say 5 as the random number, but it can be anything. The batch size is again up to on your hand, whatever the batch size you choose. And this epochs means that how many times you want to do this same thing, how many times you want to do the training over the full set of data. Okay, so say you have 1,000 points. What the computer will do is, at this point to fit is from the 1,000 thing, it will just divide the full 1,000 thing in parts of 5, 5, 5, 5, 5 set, and then all this for all this 200 sets of samples, it would do the forward pass, then do the back propagation to make sure to adapt the weights and biases, and then it would do this whole thing for 20 times. That's the epoch. Okay, is it fine? These are mostly all the parameters that you need to run your first neural network, and mostly this is all that you need in some sense. Is it fine? Is there any question so far?
I have one small question.
Sure.
So if we like, suppose if we want to give a custom loss function, then how do we include that? I mean, do we define a function and then?
Yeah. There is something called keras.backend. So you can, I mean, I'm not showing all the details, no, but
That's right.
but keras.backend is something through which you can define your custom functions as well in the TensorFlow. Okay, any custom function, if you're providing the custom function, normally you are also supposed to provide the derivative of it, because you see that fz and f prime z are both needed to do this backpropagation. It's better if you provide f prime z, or else it would just do a numerical computation of f prime z as well. Yeah, but you can do that.
And what is this? Can you just briefly again, what is this optimizer doing? So just it finds the suitable learning rate.
Right. So optimizer is doing the following. Say, so what you are having is that you are having some cost function, say C, and you want to take your C to here. So this is a huge parameter space of your this say theta. Sorry, this say W1. This is B1. This is W2. This is a huge set parameter space. Okay. Then what you want to do is take your C to some say C minima. This is the target. Okay, then what you are doing is that if you set a eta parameter, so what it does is that it would do this kind of thing to come here, right? I mean, some step size like this. All the step sizes are equal if you just set learning rate to be the same. What this optimizer does is that it would change the step size. It would start changing the step size such that you get this convergence to C minimum faster. That's the optimizer's work.
So we don't have to like worry too much about the learning rate.
Right. So I mean, in some sense, you have to, because this optimizer does not change very drastically. Say you say that my initial learning rate is 1. Okay, then the optimizer might not be able to take it to 10 to the power minus 3 or something. It just optimizes things, but you need to have a very good initial case. Okay. So once you start using these packages, your life is very simple. All the things are defined.
And these thetas that you're not initializing it.
Right. So I don't have to. So initially, when I said net compile, it started initializing them with some random variables. But as you are asking, you can, if you want, you can set all the variables. I mean, by hand as well. That's also an option. I mean, you can say that first layer put some Gaussian distribution with some sigma and some mu or something. You understand the point? I mean, if you want, you can set all these variables by hand in any possible way you want. You can either put all of them individually or just set some probability distribution from which it just sample what should be the weights and biases. That can also be done. But so far, what I have shown, net.compile, if you don't specify anything here, if you just write whatever I wrote, it just randomly initializes the weights and biases.
Okay.
Okay, good. So once you do that, finally you have to you have now you went through this batch size training, this epochs and all those things. You have done that. Now you are at the stage where you want to see how good your network predicts. So to do that, you just have to say that jali dot underscore st4 predict on batch. I said batch because you Python handles batches quite easily, and what you can do is that bunch of functions that are previously unknown to the network, you can throw them together in the network, get whatever the output it generates, and that is your out. So out j would be containing all the output of the jth sample in the batch. Okay, so this would be now the prediction. This should be now the prediction. So we went through all the steps in the code. First, how to create the network by doing this jali underscore st4. We say that this is sequential. Then we added the layers. Then we compiled it by mentioning what should be the cost function, what kind of optimizer or something that I need to do. I need to include what is my learning rate. All of the things are mentioned in the compile layer. And after that, I fit it with this thing, with there's some training data, and then I'm
Yeah.
checking what is the output
Okay. Okay.
in for some unknown data. Okay, is it fine? When these are the steps, and this is the most simple
Four
way of
zero
setting up
eight
all your
six nine
things.
nine.
Okay,
Six
is there
nine
any
nine.
question now?
Yeah. Okay. Thank
Okay, just one small,
Yeah,
very small
sure,
thing.
sure. Hmm.
So in the initial step, like when you are initializing the layers, right?
Hmm.
So suppose like I'm just asking that if we want to say initialize 100 layers, you can do that using a for loop or something, or is there a better way?
Yeah, for loop you don't do anything for. For is always taking some
Yeah.
time. But once you say Jali compile, it compiles all the layers together.
No,
You
no,
don't
no,
have
that
to
is
worry
not
about.
no, that is not what I'm saying. I am saying that
Oh,
the very beginning, like Jali ad, you did no, like
yeah, yeah, yeah.
individually.
You
So
can do that in for. Yes, you can do
that you
that in
can do
for.
for.
Yeah, yeah. That you can do that in for. But my way of doing it is normally I just define this whole all the layers as a array. I mean, in some sense, you can just do it in a single go. You don't have to do a for loop. There are better ways of doing that. But of course, you can do it in a for loop. Since because normally your number of layer would be like 10, maximum that would be 15 or 20, not deeper than that. So 20 for loop is nothing. You can
Yeah.
just do that. Yeah, that's it. Or here also you are not doing any computation or anything. You are just setting up. So a for loop is
Yes.
completely all right.
Yeah,
Okay,
yeah, thanks.
good. Good. So once we are done with that, then there's something we should remember, and these are something I learned most of them the hard way. But first thing is that training a network is very stochastic. As Anish was also asking probably yesterday that Anish was asking that is there any first principle things or anything to begin to set up all the things. There is nothing like that. So training a network is a very stochastic process. What you are setting and this thing is very random in some sense. And also you can of course you could have asked that is this training unique. As a mathematician, you can ask that whatever this thing is, are the weights and biases when finally the minima is reached, is this thing unique? Those are not unique for the same training data, for everything same. If you do it different times, I mean, do it multiple times, you can get multiple results. But most of the time, they will all have the same kind of performance. So there is nothing like a unique trained network or anything. Normally, what people does is that once they have a good trained network, they just save the network. One can just save the network in a text file or something, and then that can be reused. That can be done. And final training strongly depend on the training data, as I was saying yesterday as well. So say your input sizes, or to say so your inputs, if they are not very sparsely distributed, sometimes it happens that your network learns very badly. It does not know what to do. Say you want to fit a single dimensional function as say fx. If you just give the training data where x belongs to say 0 to 5, and even then if you ask some question that what is the value of after training, you ask the value that what is the value of x at 4 or something, point 0.4 or 0.3, it does very badly. But if you do like, if I mean, normally it does badly if the function has some peculiarities. But normally you have to spread the distribution. If you have a training data, good training data would include a very sparse amount of very distributed amount things on the data, because in some sense here, when I was talking about a function f of x, I already know in some sense how should look like, and all that was in my mind. But normally when you want to fix something like that, for example, if somebody is not familiar with it, don't worry, I'm just throwing some terms here. But say you want to have, for some Calabi or manifold, you have h1 h2, those are your dimensions of h1 h2 things, and you want to fit, you don't know what function fits does h1 h2 and all those things. But it has been observed that if you do it in the training data, you include small h1 as well as very large h1s, then the training is much better. So the training strongly depends on the quality of the data in some sense, what we're giving. And of course, the third point where what I've written is the same as we discussed. There is no first principle explanation for network hyperparameters. Therefore, the network is not a substitute for basic understanding. Although I think it might be possible to use network in various possible ways, where you can interpret each weight and bias as some things. In that case, probably network has some meanings. But while you are doing this training, say cats and dog training and all, don't normally they are not substitute for any kind of basic understanding. So you have to be really careful when doing this neural network things, if you want to really figure out something out of it. So for example, you throw a bunch of CERN data, and then suddenly you see that there is some different kind of particle speed or something that the network is predicting, and you are very happy that, yeah, I broke the light barrier or something like that. You are probably wrong. So yeah. Now this thing
So,
is yeah.
is there a canonical example of a problem that was solved using machine learning, or what sort of thing
So
are we looking
so
for?
right. So one of the example that I was just going to go there, but one example, as I was saying, that this Calabi-Yau manifold kind of thing. So what happens is that any I mean, at least the mathematical part that I can just tell you. Or is there a simple example then Calabi-Yau? Using only this thing, I cannot come up with. Oh, but yeah, one of this thing is that say you in gravitational waves and all those things, people normally they want to do some parameter estimation. So say they have some observed data which they are detecting in the detector of gravitational waves, and then they want to get some parameters which tells them that what is the mass of two black holes or whatever generated this gravitational waves. So in those cases, what you can do is that whatever data that you already have, previously have, you can just throw that, train it, and then once the newer data come, you can ask that if this thing is this so what kind of parameter estimation it may have. So for example, in this case, what you can do is you have a theoretical framework. So say you assume that two black holes are rotating with some masses, and you know what should be the detector data that it should have. So that means you have a huge number of training data. You can just change the masses and generate a huge training data. With those training data, you train a network. So now this training network is ready with your theoretical calculations to predict given an event. It now know how to predict what are the masses. Say let's focus on this black hole event. Say given what is the detector data here, it can tell you what is the M1 and M2, the two masses of this black hole. Okay, and you train it over your theoretically manufactured data. Once it's done, now given a gravitational wave, real gravitational wave data that you have, you pass it through this, and just get M1 and M2, and that's faster than any calculation, any numerical calculation that you can do by hand. Okay, so that's one of the example. It's a very I dumbed it down very much because I don't even understand how they had that hit fully. But this is the crux of the thing that people have used as well in that perspective that I'm sure of. And in mathematics, people have used this network for predicting different Hodge numbers and all. So Hodge number predictions is something. So for example, this completely intersection Calabi-Yau manifolds, the Hodge numbers are already known. So given some data, some metrics, we know what should be the Hodge number, and it seems that once you train a network, a simple network, it learns to calculate Hodge numbers from given a something called a configuration matrix. It know how to calculate this H1, H2, and that's really fast. So that has been done. Is it fine?
Yeah, yeah. Also,
Good.
the tensor networks in ADS-CFT, stuff like that.
Right, but that is
uh,
something. That's why I said, yeah, very good. So that is something a bit different, as I've said. And the tensor network and ADS safety, all those pictures. Now you see that you are associating some meaning to the weights and biases right from the beginning. So there is no point of training or anything. I mean, there are something, but we might discuss it in some later time. Okay, those are very interesting parts, but let's not go there. And let me just go through other parts, right?
Okay, okay.
We can
Yeah.
discuss it afterward.
Right.
Okay, great. The ADS safety parts, holography part, I'll just keep it here, but probably I can do one more lecture at some time where I will discuss those as well. Anyway, so let me go to some other networks. This is, is there any question from someone? I can hear the noise. Oh, okay, let's stand up. Good. So some other formal network that that we as a physicist we sometimes will use is a classifier. This classifier is something that we have been talking about from yesterday as well, between cats and dogs and all those things. So for the classifier, you can of course. I mean, at some point I tried classifying CFTs with given some data. That's a horrible story, but anyway, those classification things can be done. Now, what you can do is that say here this is the number 6 written. Forget this. This is the boundary of it, but whatever. This is an image of the writing 6. You want to put all these values, pixel values here. Say this 6 I can, or 6 or 1 I can write in a background of zeros. I mean, I can just write some 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, or yeah, 0, 1. Sorry. 0, 0. And I just said that okay, whatever I have written here, this is my 1. I'm writing 1. I mean, just if you don't want to go to pixel values, you can do that as well. Whatever it is, you put these values of this input, values of this picture here in the neural network, and what you want to achieve is the following. If it's 6, you want so at the output you want to observe some 10 nodes. Okay, and then if this is 6, this guy should light up, or just say 1, and all of them else should be 0. Okay, this is something you want to achieve. So if I write 1 here, it should understand 1 by just telling me that okay, this is 1, and then all of them are 0. Okay, these are called category classification, and also this thing of doing, as I'm saying here, these are called one hot encoding, because one of them is hot and all the else are very cool. So that's called the one hot encoding. So to do this one hot encoding, what you want to achieve is, I mean, this is what you want to achieve. Now, how do you do that? Now, normally the network generated, as we have seen, that network output are some function f of x, f of z that you do at the very end. So that is normally some floating numbers. Okay? It can take any values, but what you can to achieve, what you want to do is that, say you want to classify n number of events or n number of things, and then to classify this n number of things, what you want to do is that you have to assign some probability assignment to each of these nodes. This probability assignments, whichever have the maximum probability, you said this is that. So for example, here n is, let's say, 10. Then I say, okay, I'm inputting my handwriting as 6. So 6 should be some values here. Then it should, values in the input. It should generate some output. From this output, from this output, you want a probability distribution where the sixth node will have maximum probability. Say 6th node has the probability of 0.7, and the rest of them is 0.1, 0, something like that. You want to have something like that. So to do a probability kind of definition here, what you can do is use this function. Is this function familiar to you guys? I think you have seen this kind of things everywhere. E to the power something, and then sum over all the e to the power something. Yeah, I hope in statistical mechanics when you partition. Anyway, so here what you do is that this fj, if you set this thing, so once you calculate what is the output values, the z values at the output, rather than having a ReLU or whatever function that we know we have used so far, you can use this function. What this function is that does is that all of this output fj's be automatically between 0 to 1, and if you sum over all of them, it's 1. So it's basically normalized and non-negative as well. This is called a soft max activation. So in your last layer, as we have said, in the very last layer, we said jali dot add something linear, if you remember. So here what you can do is that if you want to classify in number of objects, in the very last layer, you just said jali underscore st4 dot add dense with in number of layer, and the activation is soft max. So once you set that, what happens is that the output is always, you can interpret the output as some probability distribution, some values between 0 to 1 for each of the nodes, and for whichever is the maximum, you say that's my output. Okay. Now for any probability distribution, in principle you can define something called the entropy of the probability distribution. Okay. And here, already 4:13, so I'll be a bit faster. So here what you can do is something like this cost function, you can set it to be some pj target log pj. So pj target is what should be the value of the pj. And here the training is that you have bunch of images of handwritten images of 1, 2, 3, 4, 5, 6, 0. And then they are also having output 1, 2, 3, 4. It's already defined. Those are your training set. You are throwing in that as the training set, and you say jali underscore st4 dot fit. Then while fitting that, what it would do is that the output 5 or 6, it will digitize in some way. What you to do is that if you say 5, it will do 0, 0, 0, 0, 1, 0, 0, 0, 0, 0. Okay. So in that sense, that would be the output. So if you do this cost function, you can see that this is minimized if pj and p target are same. This is also probably something that you guys have log p kind of thing, this entropy, Shannon entropy kind of thing. People are probably already more familiar than me. So there you see that if those two things are the same, then this cost function is minimized. So this is a new cost function. So to this kind of cost function, this is also very easy in TensorFlow. Rather than writing mean squared error, you just write categorical cross entropy, because this thing is named as categorical cross entropy. Once you have this categorical cross entropy defined, your network is ready. It can now classify things. Okay. So this cat dog thing, cat dog conundrum, you can solve it with this thing. But you have to be very careful about. I mean, there are some warnings. First warning is overfitting. So overfitting is something that happens pretty regularly. What happens is that, say, if you have a large number of training data, and then you have increased your epochs. That means you are retraining and retraining over the same network several times. And what happens is network gets obsessed in some sense with the training data, and it knows with very intricate details what are my training data. And that's bad for you, because now if you introduce some unknown data to the network, it fails. It cannot predict what should be the output, because it just knows this training data very well. It does not know what exists outside this. Something might exist outside this network, and that happens. This overfitting happens almost every time, I would say. If you really want to start doing this thing, this overfitting will happen almost every time. So to do that, there are two ways of getting rid of overfitting. First is early stopping. Early stopping means that apart from having a training set, you also have a validation set. Validation set is something that you know what should be the output, but you haven't told the network. So you just thrown it some training data, and you kept some data personal for your personal use as validation data. So you train the network, then see how good it does with the validation data. Okay. Then once you see that, okay, this is now this has reached some maximum of value, maximally good parts of performance validation data, and then the performance or the prediction is getting decreasing, then you say, okay, now it's point to stop my training. So that's called early stop. That you can do, even if, although you put my epoch to be 100 or 200, it would train and retrain 200 times. But once you see that your data are more or less fixed, you can just stop there as well. Okay? That's called early stopping. Or yeah,
Okay, so when we are this overfitting is happening, that means the predictions will become very bad, right?
right. Prediction is bad in a sense. For the training set, the prediction would be superb. But for the newer number, the prediction would be very fat. That is validation. So that is overfitting.
Okay, okay. Like if I have like if my network has been overfitted, so how do I know that? I mean, say I am
Yeah.
not so knowledgeable and I just give some data and the result I got is a overfitted result. So how is there any way I can understand that I have
Yes,
committed?
yes, yes. Because whenever you are putting some training data, yeah, you would not use all the data that you have in your hand as training data.
So
But
in
you
that case, we have to do this validation.
right, you always need to do validation. What you should do is that you always need to you suppress some of your part of your data just to do the check that if things are working properly or not. Before you start predicting things, you have to make sure that things are working properly, right? So if you have 10,000 data, keep 2,000 data for yourself. Put 8,000 data for training purpose, and once the training run, and see how the machine works against those 2,000 data. Okay, that's validation, and only through the validation you know whether there's a overfitting or not. Because if you have only 10,000 data, you fitted it very well with your network, and then if you ask a newer point what should be the output, it would give you some output, but you don't know whether that is good or not, right? With the validation, if the network does good with the validation data, that means you have some confidence on the network that yeah, this is something doing something good. Okay.
Okay.
So validation is very important. And one more thing is dropout that Anish was also asking about. We have seen somewhere that putting, even changing a pixel changes the output kind of thing. So here, what you can do is actually do some dropout in a sense that you just randomly put some neurons to zero. Okay, that what does it do is that it does not let the network learn all the features in some sense of the training scheme. So there is always a noise that this network have to handle. There's always some extra or some reduced information that the network have to handle, and that is random. So that means in some sense it's that it knows there something exists beyond this training set as well. So sometimes this dropouts works better. So most of the time now people what they does is if they have a huge network, they put Gaussian dropouts by hand. Gaussian dropout means you just introduce some Gaussian noise, and Gaussian noise is some Gaussian, you just sample some random network from a Gaussian distribution and put them to zero. The number of the and that is something that people are now doing as a good practice. So this is another thing that if you once started working on, you would come across this.
Just one thing. When you are saying noise, so what is this noise? I mean, it is noise in the training data. Uh,
Yeah, noise in a sense that whenever I am disturbing something. So if I'm just putting some trained neuron, say after a training, there is some neuron has got some value that might be important for the network, that particular value, but you are just putting it to zero. So you're introducing some disturbance to the network. That is what I meant by noise.
Acha, this is not the same as say sometimes what we do during this basic car fitting, that we add some noise to the data itself, like some
No,
Gaussian
no,
noise.
no, 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 no. That is some form of cleaning and all this. That also can be done, but that is in the input data. I mean,
Yes.
in the training data. What you are saying, that would be in the training data as well. This is not that in the part of the training data. This is the part of something inside the neural network. You're just putting something to switch off. In some sense, they are equivalent. In some long hand waving sense, but what I'm saying is something different. It's inside the network. Is it fine?
Yeah, yeah. So I'm just trying to understand what this means. I mean, you are trying to add some noise to the network itself.
Right, exactly. Such that the network never learns. Basically, So the problem is that some overfitting is basically your training data, say whatever your training data network started learning with 100% accuracy, say. Okay, so that means it knows the training data very good. That there's a tremendous possibility in that case that if you put some data other than the training data, it would work really bad. It's been observed. So that's why this is like a way out in some sense. One of the suggestions that people would do. There is no a mathematical way to convince that that would avoid overfitting for sure. But this is as a good measure. People are just doing Gaussian dropouts now. Okay.
Yeah.
Yeah, good. So for the time being, I would skip convolutional network, but I just want to mention something. This convolutional neural network are something like they try to learn what is the symmetry of the data. So for example, here, if you put A here or A here, these are both of them means the same thing, but they have some different position. Okay. And now this is same as something that we do in our mathematics as well, so that we do this convolution and all, but I will not go there for the time being. One of the interesting part in this convolutional network is that what you say that, okay, only this part of some layer affects this layer, this neuron. Normally with a dense layer, what happens is that all of these neurons affects this neuron, because all of them are normally get connected. But what you are saying in convolutional network is that, okay, only this part, some adjacent part, they are disturbing this guy and nobody else, and that comes out of some translation invariant and all. And I will not go there for the timing. I will just they just have very little time. So for the convolution network, interesting part is that in convolution network for engineers and all, what they get is translation invariance or rotation invariance and all these things. So one of the things I was interested, I'm still interested in, is that is there any way to incorporate gauge symmetries like this and some sense. But that I would discuss if somebody has a question or want to discuss afterwards. That how can it be done. But there is no good answer to this question as of now. At least I don't know how to incorporate gauge symmetry. But people are looking for network which already have some gauge symmetry, which can deal with gauge symmetry. If your data has some gauge symmetry, it can deal with it. Good. So far, I was talking about supervised learning because all the training data is about supervised learning. So that means I already know what feature I want to extract. So in my example, I had the size of my glove, size of my shoes, and then I want to extract what is the height. So I already know what are the features I'm looking for. So it may so happen that you have a huge number of features of some cats or dogs or something like that, but you don't know what feature you are after. Or you can ask a different question. I'll come to the different question in afterwards. What kind of other question that you can ask the same question, same network. So unsupervised learning is somewhere you don't set any training data. You just have some data, and that's you just want to figure out what are the features and all on this data, or is there something in this data that might be interesting to me. Okay, that's the question. So there are a lot of unsupervised learning, unsupervised learning networks that are there, but mostly I am for my cases I'm mostly interested in something called autoencoder. That's why I will just introduce autoencoders as the unsupervised network part. So in autoencoders, what you say is that, okay, whatever output you are generating, that is equal to input. You are saying that output and input are same. Then you might think that this is very trivial, right? I mean, if output and input are same, then this should be like a direct connection and it should just give some trivial answer. But what a non-trivial thing that you are doing is, see, you are decreasing the number of nodes. Okay, so in some sense you see that if this picture needs say 900 nodes to get the data, and I'm minimizing it to 2 nodes and then again reproducing this 900 nodes. So that means the information of this full 900 nodes is basically inside this. Two nodes that I have, right? So this is called a autoencoder, which learns basically itself. And this is called the latent space, where these values are there. This values captures all the details of it. If it's the faithful representation, I mean, if you can reproduce this input in this output, then That means whatever data that you have in this layer, which is called the bottleneck layer, is sufficient to reproduce this guy. Okay, so this kind of network you can use as a as one of them is one of the uses is that you want to suppress a compress image. Say you want to do an image compression. You want to take a picture and want to minimize it to some smaller size, or you want to store this information somewhere. Okay, then what you can do is you can do this kind of autoencoders. You put your image here and get your image out, but and each time you minimize this thing, minimize this. And now see, although this is unsupervised, I'm not providing any training data or anything, but you see, you can think of it as a training as well. This is in some sense as a supervised. You can just think of unsupervised as a supervised network where the inputs and outputs are same. You can use the same mean square cost function and everything. Okay, the idea is clear, right? I mean, it's a very simple network, most simplest probably for unsupervised part. And normally the bottleneck size you keep on decreasing. For example, say if you have 900 nodes, at first you start with say 100 nodes in the bottleneck. If it reproduces it accurately, then it's fine. You minimize it to 99, and so on and so forth. Once and you will see that the more you minimize this guy, your picture, that the reproduction would be less good. I mean, the reproduction will not be very faithful. And you set a, let's say, error threshold or something, that okay, if my picture gets damaged by 50%, I'm fine with it. Then you know what should be how the compression, I mean, what is the compressed version of it. Okay. So this part is called encoder because it encodes all the information in this layer in this small space, and this part is called decoder. Okay. So normally what you do is that once the training is done, you can cut this network open and use this part as encoder and this part as decoder. So if you want to send a secret message or something, you can write a autoencoder to reproduce your messages. But of course, you put some values. If you put some less number of characters here, so if that is getting faithfully reproduced, that means you have a if you have a encryption, and this encryption can only be unencrypted through this part of the networks, because this is very non-linear. Okay, so this is one example of unsupervised learning, where there is nothing like a training data. You just have some set of data. And this is something similar to what people use in statistical mechanics called principal component analysis. So say you want to measure what are the most important qualities from a set of data. This is your guide. You just minimize these things and see if that gets reproduced or not. Okay. And then I will go to the last bit of for today, that is called is there any question with the unsupervised part? Then I will just go to reinforcement and finish. Is there anything with the unsupervised that you know? Good. So I will go to reinforcement now. So reinforcement learning is something that people are using extensively now, and this is somewhere I think that a little bit of coding and all is needed. Otherwise, you cannot visualize what exactly is happening. But reinforcement learning, the basic crux of reinforcement learning, and not crux, I mean, the need of reinforcement learning is the following: that if I have a data, or if I have a set of training data, but maximally the network can learn is as good as me. For example, say I recorded my chess playings, okay, and then I take those my chess moves as training data and feed the network. So network would learn how I play the chess. It cannot surpass me. So it's like a student-teacher relationship. If you're always a student, if you just go to your teacher and start asking questions, it will never learn more than the teacher. So you have to be creative on your own, and then you have to be like what people call a scientist. So you do your own mistakes and you learn from your own mistakes, and that's the same principle in some sense in reinforcement learning. What happens in reinforcement learning is that you are you are making something called an agent. They name it a agent, or some algorithm which takes some decision. For example, let's say you have to play some card games. So card games is basically left and right. I mean, you want to go this side or that side. Some game of card. Some card. I mean, it's a very old game. Think of it. So some cards that, or think of the example of a snake. Snake game that you all have in old mobiles and all. So snake is what that you have a this little snake guy. We have to go and then eat some whatever pixel blinks, and then it get its body stretched, and so on and so forth. It have to go through the whole maze. Okay. Now the decision that you have to make every time is that what should be the in the next step, what should be the direction of the snake, right? So it's just mostly you will have left and right, left, right, or up, down. These are the only options that you have. So standing in the direction, you can only decide either go this way, that way, or this way. Three options. So say what you define some algorithm and name it as agent. What agent does is it looks at the environment or the whole screen of your mobile and take a decision whether to go left or right or go straight. Okay, and then it does this thing unless and until the game is finished. So that's the agent, and if the game is finished, you say that okay, you get some reward. That agent wants reward in some philosophical way. That's what you want to do in your calculation as well. So in general reinforcement learning algorithm, that involves an agent who observes the environment and takes some action. So for example, in a self-driving car, the car itself is the agent who looks at the environment, which can be the traffic condition, and takes the action, which is the movement of the steering, clutch, and gear. Okay, so that's the relationship in this reinforcement learning algorithms. But for physicists or mathematicians, for us, the solution space. The actions can be some domain or from where you are getting some sampling, some data point, and then the reward can be solving some equation. If you solve the equation, you get more reward. If you don't, you get less number of reward. That is one of the good paper that if you want to read is that learning to unknown. That's I would say moderately well written paper for beginners as well. You could understand what exactly they are doing because they are comparing several things. And if you don't go to the coding part, you just try to understand what exactly they are doing. There you see that but the target is that given a knot, which is very complicated, then it just asks the agent to unknot it, or let's just say that whether it's a unknot or not. I mean, is it a unknot or it's not? So that's what the agent does, and it seems that if given this task to us, we developed, for example, different knot polynomials and all to see what are the crossings and all those things. And then we have this moves to slowly uncouple all these things very cautiously. Now, what happened is that this reinforcement learning algorithm, the strategy that their reinforcement learning developed, also involved knotting it more. That was very strange because they haven't told it to knot it more. I mean, there is a knot. Rather than pulling the knot out, sometimes it make the knot more difficult and then start unwrapping it, and that helps it. It's a good move that the network learned on their own. So this is a strategy that the network learned itself and surpassing whatever their teachers were doing in some sense. Okay, so that's the reinforcement learning. So reinforcement learning is basically agent which looks at environment, takes some action. Looks at environment, do some observation, and takes some action. Okay. Now rewards can be short term or long term. I will give an example and finish. But anyway, here the rewards can be long term or short term in a sense that, for example, a game, the snake game, the decision of going left or right or straight does not make you win the game. So you can give a short term reward. We'll say that okay, if you are doing left, it's fine. Okay, man, just get this point, and right this fine. Just take some point or something like that. Or you can give it a long term reward, which is that if you win the full match after this full set of decision making, once you either you die or you win the match, I will give you more points. For example, say the snake, if the snake dies after getting long enough, then you get more points rather than the short length snakes dying dead short length snakes just give a small reward, that kind of thing. So the goal is this thing, that your agent, which is your reinforcement learning agent, would look at your environment, say the traffic condition, for example, then looking at the state, it would take some action. That action would again directly affect the environment. And after looking at this effect, it would do this same observation and do this thing again and again. Okay. Then what exactly the neural network thing comes into the picture is this part. So this state to action thing that it's taking, this is called policy. So policy is basically given the state what action it should take, and that action taking is also some it depends on some probability distribution that people do. I will go there. The probability to pick some action AT given observed state ST. So here you can think of your snake game as well. It looks at your monitor and this take a and looks at the state and take a action either left and right or moving forward with some probability. Say given this state, the left moving to left, that probability is 0.3, and moving to right, let's say probability is 0.6, and going state is 0.1. So on that probability distribution, it would just sample one action, and that action will be taken here. Okay. Good. And normally, what the neural network comes into the picture, the state to action thing is taken by a neural network. So the policy is normally a neural network. Okay. That's one of the, I mean there are several variations of it that we might discuss afterwards, but one of them is just using one single neural network in the policy. There are networks, there are algorithms where this environment itself is also a neural network. Let's not go there. For a very simplistic case, you can have one single network here. So one of the example that I would give and finish this this set of lecture is that solving a differential equation. So before doing that, I need to warn you guys severely, because this example, not even an example, I just give an algorithm. This algorithm not works for any differential equation in any given range. That it does not. It's a very narrow set of domain where this thing works first. And there are several intricacies here which I will suppress just to give you the overview of what exactly is doing. Okay. And if you want more further details or something or example, that I can tell you with I have a code as well to just give an example. But anyway. So let's say your target is that you want to solve this kind of thing, where you have this u is basically your function, desired function, which you want to solve as a function, and this ut means the derivative of u with respect to time. U is a function of x and t. X can be single dimensional. For example, you can think of x as just x and t. Don't worry about the vector sign. And this n is some nonlinear operator parameterized by this variables v. It can be anything basically. You can think of del t, del u, del t plus some derivative with x respect to x, and all these things are physical. Now, once you do that, so to solve the differential equation, you also need boundary conditions or the initial conditions. Then what you can do is take this following set of steps. You just start with a domain. So normally, if you guys are familiar with some numerical calculations, how do you solve this differential equation? Is that you get a say one-dimensional differential equation. What you do is that for a given value x, you do this Runge-Kutta method or whatever, get what is should be the output at that point, plot that, and go to the next point, plot that, and so on so forth. Right here also, this t is the dimension direction with which over which we are to solve it. So first you start with take your t in between 0 and some delta t. Delta t can be anything you choose in your domain, and break that delta t in parts. In again depends on you. Capital N can be 100 or 200, depends on you. Then you take this as your domain, or this domain is basically your state in some sense, as I was saying. So these values, you put this in the neural network and get two outputs. One is the mean value, one is the standard deviation. From this mean or standard deviation, you just sample a value out and you call that value to be your solution. Because here what you are doing is, in some sense, you are mapping this thing, you are mapping from a domain of x and t to the solution, the domain of solution u x t. So that mapping, say this mean value and the standard deviation, that captures that probability distribution, and from that distribution you just sample out one point and see how this sample solution works. So here you can say that your reward function itself is how good you are solving the equation, differential equation, plus how good you are solving the boundary conditions and so on. Okay, you can just say that those are my reward functions. With those reward functions you can update the neural network again for you can keep on updating the neural network such that with the same this domain such that this reward goes to some minimum value of 10 to the power minus 4 or something. Say if this is 10 to the power minus 4, that means this equation is getting solved with 10 to the power minus 4 accuracy. Okay, once you have done that, you go to the ti plus delta t. That means you go to the next set of steps. So if you do that, what at the end of the day, what you have is that for each point t, you will have a solution, and you can do the plot. That's the algorithm. For example, that if you think of something like this is called the Van der Pol equation. This is in the same format. It is a double derivative with respect to time, single derivative, and all those things. So if you do that, there you cannot even see this blue lines. You can see the blue lines in some places. Those blue lines are the solution you get by numerical solution, and the red is basically the neural network solution. So red and blue are exactly matching in some sense with the same algorithm. Okay, and I'll just finish by one sentence that at some point I here in this set of lectures I just only discuss everything about things about machine learning and how we actually can work with that, but I haven't discussed anything related to actual string theory, physics, or something like that. But I think that requires more time, so that is something that we might discuss at some later lectures. Okay, so I'll end here.
Yeah, that will be very nice. You can do
Good.
that sometime.
Yeah, sure. That I'm also interested. So I would deliver that at some point for sure.
Okay. Good.
Okay, so can I just ask something that I maybe
Sure.
missed it? So there's a previous slide, if you can go.